Hey guys, welcome to VT GeosChat. I'm your host, Rose McRorty, and this week I'm excited to share that we are joined by our fifth year PhD candidate, Ben Eppinger. Ben is going to be sharing us his research in the critical zone, and specifically his research paper is titled On the Role of Inherited Rock Fabric in Critical Zone Porosity Development. Insights from seismic and anisotropy measurements using surface waves. That's a mouthful, Ben. Can you tell us about it?
Yeah, of course. Thank you for having me, Rose. And I love to break down that title a little bit. So yeah, on the role of inherited rock fabric in critical zone porosity development. So I think the first term that we could to de-jargonify would be the critical zone. Okay, so yeah, so as you know, but maybe they don't. The critical zone is a very broad area of Earth's terrestrial surface. Basically, anywhere you go on the Earth's terrestrial surface, right on land, that is from the top of vegetation down maybe 30, 40 meters into the subsurface where bedrock is really intact and really hard. That's the critical zone. So basically, the critical zone encompasses terrestrial life, right? Vegetation, critters, what have you, and also, encompasses the soil that vegetation is living in and inhabiting, and also basically the rocks that are storing and transporting the water that the overlying vegetation is relying on. So if you think about it, we all live in the critical zone. We all do things in the critical zone. We grow our food and farm in the critical zone. We get a lot of our groundwater from the critical zone. We build in the critical zone. So it's a very important area, for us humans and for other terrestrial life as well. And that's why we call it critical.
We're not at all biased here. It's critical to us. But that's a really great introduction to the critical zone. So you were looking at porosity development. So that's pore space, open space in the critical zone. Can you tell us, though, why that matters?
Yeah. So my favorite thing about the critical zone personally is how it turns, boring, to me it's boring, tight rock
Matter of opinion.
into beautiful soil. So if you've ever seen like a rocky cliff, a rocky outcrop, you usually don't see a lot of very productive vegetation on it, right? But most of the productive areas that are really good for biological activity on Earth's terrestrial surface are places mantled by soil, right? So what's happened there? And what's happened is, this amazing process of weathering, where you basically take, rock, right, what you might grab out of an outcrop or up from the top of a mountain, right? And you basically break it down into soil, right? So critters and animals and plants and flora and fauna, they have a much better time living in soil than they do on bare rock, right? And the key aspect of that transition is the development of porosity, right? So how much empty space is in a material, right? So if you take a rock, right, all the little holes and cracks in it, right, that might account for maybe 1%, 2%, maybe 5% of the whole volume of the rock. But if you take a handful of soil, right, it might be 50, 40, 60%, right? Open space where roots can go, open space where worms and bugs can go, open space where water can be stored, open space where, gases and air can be stored. So porosity is the key variable that distinguishes, right, weathering, right, that distinguishes basically very productive soil from not so biologically productive rock.
So, and you're saying that with this porosity, you're also saying that there's groundwater in the porosity.
Mm-hmm.
So I would imagine that this is pretty important for us as people because we drink water.
Yeah.
And so we're very dependent on this, but it also would impact, I would think, stability.
For sure. Yeah, so just to build on that first point about the water, of course we use the water, right, or animals and plants use the water, right, but also the water is flowing through the porous material, right? So this is very important if you work in the environmental consulting industry space. So if you spill something, right, something toxic, something hazardous on the surface, which unfortunately happens, fairly frequently, right? And sometimes it's like unavoidable, right? So for example, like a landfill, right? You're going to have a landfill, you're going to have all this water matriculating through the landfill and interacting with all the garbage there, right? And then it's going to go somewhere. It's going to flow in the ground, right? And where it flows is determined by the porosity of those materials in the upper 10 to 30 meters of the subsurface. So just from the aspect of managing water, understanding water, and keeping that water safe for drinking and safe for ecosystems, right? The porosity in the near surface is important. And also the aspect of building on it, right? So basically you can imagine if I took this table, right, which has very little porosity, it's pretty solid, right? And then I removed half of the material from it, like I put all these holes in it and made it Swiss cheese, it'd be a lot weaker, it would break easier, right? So how much porosity that's in something, that's very important if you're building on it or if you're thinking about hazards such as like landslides.
Okay. And so what exactly are you trying to study with this paper? You're looking at this porosity in the ground. So are you measuring how much porosity is there? Are you measuring how the porosity develops or how this material evolves? Like what exactly are you looking for in this study?
Yeah. So past research has sort of like investigated and sought to understand this key role that porosity plays in developing the critical zone, right? But what we're trying to do is we're trying to add a new wrinkle to that, a new detail. We're trying to understand how is that porosity structured, right? So it's kind of understood that, soil is going to have this much more porosity than rock, right? But we don't necessarily understand like how is that porosity in the soil organized, right? Because basically you can have 50% porosity in something, right? But if you organize that pore space differently, you can have a material that's much, much weaker or much, much stronger, or can allow water to flow much, much faster or much, much slower, right? So we're trying to understand the structure of the porosity within the critical zone.
Okay, well that's pretty interesting. And I would imagine that this is very important for humans as we're thinking about human development and expanding our urban areas and our human think about how we live and grow and how we grow as a society in this critical zone.
Yeah.
I would imagine this is pretty important for that kind of growth that we want to see as a society.
For sure. Yeah, definitely as we want to understand hazards better, understand our built environment better, understand sort of things along those lines. This will be an important characteristic of that.
Okay. Well, can you tell me how did you do this research? So I know why it's important, but can you tell me how did you do this?
Okay, so there's sort of two aspects of the critical zone, both having to do with porosity that we want to understand. One aspect is how much porosity there is. Another aspect is how is that porosity organized. And in order to get at both of those aspects, we used seismic methods, right? So basically, seismic waves are in the ground. If you've ever felt an earthquake, you felt a seismic wave. Actually, was in Connecticut this summer when I felt my first earthquake.
Oh, nice.
It was the New Jersey one. Yeah. So anyway, so seismic waves are mechanical waves. So you can think of them kind of like sound waves, right? So when you talk, you vibrate the air. Those vibrations travel to somebody's ears, right? And then they can hear what you're listening to, right? Basically, when energy is produced in the earth, that energy travels as mechanical energy, in the subsurface, right? So what we do is we set out a bunch of sensors, right, called geophones. You can think of them as like microphones, except they listen to the earth, not people, right? And then we produce some seismic energy, and we listen to how that energy is recorded on the geophones.
So you say you produce seismic energy. Are you setting off an earthquake over there?
No, we have a sledgehammer, a 12-pound sledgehammer, and we hit the ground with it, and that produces.
You just go out with a hammer and you just hit the ground with a hammer.
We look pretty goofy doing it. I'll be honest. Well, it depends who you are. Some of us look cool, some of us look goofy.
How do you decide who hits the ground with the hammer? Do you draw straws or nose goes or?
They usually just point at me and
you get to do it a lot.
Yeah. They usually say you look like somebody who should be doing this.
That's great. I love it. So you generate some seismic energy. What are you're listening for these waves, these mechanical waves similar to sound waves. How are you distinguishing? Are you using timing, or what are you listening for? How are you doing this?
Yeah. So basically, it is a timing thing, just like you said. So you can think of it, right? The energy in the ground, the seismic energy in the ground, it is a lot like the energy, like the acoustic energy in the air that travels as sound waves. So a good analogy, I think, is to think about a guitar and how the different strings of the guitar produce different frequencies, right? So the thicker strings produce lower frequencies and make lower tones, and the thinner strings produce, higher tone energy, right? When you're listening to music, right, all the strings are being like plucked and strummed at the same time, and all those different frequencies are like jumbled together, and it's beautiful and great, just like a recording of, the Earth is great, right? When you're looking at the recording from your
Right.
geophone. But in order to actually get, the structure of the Earth out of it, what we have to do is we have to basically separate all the different frequencies from each other, right? So just imagine you could like have a recording of the guitar, and then you could kind of see, right, when each individual string is being plucked from the recording, if you can separate that, right? So we separate that, and then from that information, from separating all the different frequencies from each other, we can get a picture of the subsurface. We can get two pictures. We can get one picture, or we can get two complementary pictures. We can get a picture of how stiff the subsurface is, which directly relates to how much porosity there is in it. And then we also can get a picture of how that porosity is organized, right? There's basically kind of a number that we can map throughout the subsurface that tells, is that porosity organized in like layers, right? Or is it organized kind of randomly?
Okay. And so you're saying that as this energy is moving through the ground, and we've got these different frequencies, so you're saying things like air, for example, would they be moving faster or slower through the air? Would they be moving faster or slower through the water, as opposed to the soil or the rock? Like, how are you determining? How are you using this to find out what's there?
Yeah. So how do different things affect, the way seismic waves travel, right? So what I always tell my students is that the way you can think about it is that if something is easier to like deform, like squish with your hands, then the seismic energy is going to travel through that more slowly, right? And then if something is stiffer, right, so it's harder to like squish and bend, right, then the seismic energy is going to travel faster, right? So if you think about it, right, just going back to our handy table right here, if right, like I can't, like if I try to squish it, right, I can't, right? It's really hard. So seismic energy is going to travel pretty fast through this table. But if I had like a piece of rotten wood, right, or even if I put a bunch of holes in this table, right, like if I replaced half of the table with holes, right, I could actually probably like make the table give a little bit, make it bend a little bit by putting my weight on it, and that would mean the seismic energy is traveling slower, right? So basically, right, if we see that there's more porosity in the subsurface, right, that seismic energy is going to travel slower.
Okay. Well, that's pretty interesting. So you're kind of telling us how we did it. What were your results? What were the big eureka moments from this study?
Yeah. So the really cool thing from this paper is that we sort of were able to understand in a new way how the porosity in the critical zone is organized. And we were kind of able to show that basically the porosity in the critical zone is organized in such a way that it's a direct consequence of the geologic history of the rock that is weathering, right? So, where we were, millions and millions of years ago, right, that rock was, part of orogeny, where two tectonic plates were squishing into each other and mountains were being formed, right? And since then, the mountains have been eroded away, they're lost to time, right? But the geologic history of that mountain building event, right, is still recorded in that rock, right? And that same geologic history affects how the porosity in the critical zone develops, right?
That's pretty interesting. So that's what you were able to find out from it. I do have a couple just general questions. Can you tell me, like, what do you think were the strongest points of the study? What stands out to you and says this is a very strong scientific study that's very trustworthy, and that we did very well as we did it?
Well, that's a great question. So, one neat thing that so in this study we used multiple data sets together. So we used, I think three different data sets. So we used some kind of conventional geotechnical data set where we laid out an array of geophones, and we got pictures of the Earth that way. And then we also dug a trench into the critical zone, we dug like 3 meters down, and we got some direct measurements of the critical zone on the wall of that trench, and we were able to sort of corroborate those two measurements together and see that we were getting like the same results both ways. And then we also had a third measurement from a hole that was drilled for a groundwater well, and we were able to corroborate our results with those measurements there. So we kind of had 3 different lines of data that was independently collected and independently analyzed that all pointed to the same thing.
Okay. Well, that's pretty good. That's very convincing to me, at least. Can you tell me, I know we don't really like to talk about this in science, it's kind of a downer, but, science needs to be transparent and we have to be upfront about these things. So can you tell me what were the limitations of the study? What were things that you could have done better or that just could have gone better or that you wish you had been able to do?
Yeah, I really wish that, we could go to more places and understand more generally how geologic history affects,
Yes.
the critical zone that we all live in and build in and depend on today. So we were only able to go to one study site, and, because we had 3 different data sets that we were combining into this one study, that's all we could do in this paper. We only could look at one area in South Carolina. But I think it'd be great to go to different areas, different places with different geologic histories, to sort of understand from a more general sense how porosity is organized in the critical zone.
So you had 3 different ways of measuring what you were looking for, but you only did it in one geographical location.
Yeah.
And you wish you could go to more locations to do that.
Yeah.
Is that a time issue, a money issue?
All the
above.
Yeah. Everything costs time and money.
Right.
It costs time and money. So it's I think it lends itself, like it's something easy, like it's something we would want to pursue in future work if we're able to get more funding. It'd be a great thing to do.
Great, and that's actually a great segue into my last question. What is the logical next step for this, either for you or for other people in your lab, or maybe if any of our viewers are really interested in this and are interested in going into seismic research and would like to just try this out for themselves, what would be the logical next step for this kind of research, going off of this paper?
Mm-hmm. Yeah. I think it'd be. I think being able to adapt sort of the methods that we show in this paper, that we show work, kind of that we've developed, basically a big part of what this paper was, showing that, if you collect a certain type of data set with certain type of characteristics and you apply a certain flow of processing techniques that aren't commonly used and never actually used in the, in the critical zone before, right, you can get this interesting result and you can kind of elucidate or reveal this new characteristic of the near surface that we could never reveal before. So this is really a very novel study for that reason, and it's something that we've only been able to show for the first time in this one place. So I think being able to apply this particular method in other places would be super promising and super exciting, because you're almost guaranteed to see something new and to learn something new.
Okay. Well, that's pretty awesome. So it sounds like there's a lot of great opportunity for future research.
Mm-hmm.
Yes. Well, that's awesome. I love hearing that. I love hearing that our research opportunities are booming, and
yeah, for sure.
both literally in your geophysics research and figuratively. Unfortunately, that's all the time we have for today. But thank you so much for being on the show. It's great having you. It's great learning more about your research. I can't wait to see what you and your lab publish next. And to our viewers, thanks so much for listening today. Stay tuned for our next episode next week. And as always, stay lava.